All right, hello everyone. Getting started. Just give me 1 second. I'm still trying to make sure everything is set up on my end. In terms of my cameras, I have to keep track of multiple. Um, Sorry about that. So we are getting started. I'm just working on making sure that my camera, my whiteboard, is good to go because we will be using the whiteboard today. Talk about what we're going to discuss. So I know I'm not on camera yet. Give me 1 second. So, broadly, I can answer questions. I can't look at code in groups. That's so, like, with office hours, I always do one on one, even if it's a similar question, because it involves often looking at code in a way I can't do it. If you do have a concept question, Piazza may actually be the better place for that. And it's just because if you post on Piazza, everyone can see it, and if it's a concept question, that might be the most efficient route. Because with office hours, I will not meet in groups, just due to a potentially needing to talk to people one on one, and b potentially needing to look at code. So, just some notes. Homework 2 is of course due today. You can submit up to 2 days late, 10% per day. Understand that if you submit at 11:31 p.m., that is 1 day late. So do be aware of that. Um, Homework 3 is now posted. That will be due Thursday, and you may think, wow, that's a really fast turnaround time. But homework 3 actually does not have much code writing at all. Very, very rarely do I see it take longer than like 50 new lines of code. There's some copying and pasting of your old code. You're gonna move things around. Um, all right. Just a note with the office hours queue. You don't get to post in advance because I've done that before, and students just haven't been there at 3:30, and then so you get to post starting at 3:30. If it gets to a point that I have to manage the channel permissions manual like that, I will do that. But you need to actually physically be there uh, at 3:30. It's just posting in the queue 2.5 hours in advance is not something that we're gonna do. Um, so that's anyway. So today we're going to do. Well, first let me finish the announcement. So the exam. Last I checked, we still only had the multiple choice graded. I need to check with my TAs. I don't know the state of the coding question grading. The grade that you saw on Sunday morning, that was out of 80. That was only the multiple choice portion. Um, the coding portion is 20 points. I don't know if that's graded yet, as I was focused on getting up other homework grades this morning. You should see on Colab your homework 0 and homework 1 grades. Uh, those are now factored into your grade. We will get the exam up into the grade book soon. You should see most of your daily activities so far. The quizzes I also need to get up into the grade book, so I will do that. My goal is to do that today. Um, with the intent of by Friday, you should have a reasonable. Um, you can ask questions about multiple choice on Piazza. That's fine. Um, there's no problem with asking on Piazza. I think there was actually one question I maybe have intended to throw out, but I can't recall. In either case, those types of questions are always fine on Piazza. Just from the standpoint of office hours time, mostly being about homework grading or homework help. So we will try to have you with the best picture of your grade. What was the average on the multiple choice? Actually, come to think of it, I didn't look. I looked at the distribution, but I didn't actually specifically look at the average. I don't tend to post the average. I tend to post the median because the average bends to outliers. Um, I had to approximate it. mid 60s, maybe high 60s. It's I don't want to necessarily say that yet though. I'll give the exact number on Piazza later. Um, but the goal is to have you with a reasonable view of what your grade currently is come Friday. I mean, out of 80, not percent. So like it was like high 60s out of 80, which mathematically would put it um certainly like in the I think low 80s as a percentage, but I'm not certain of that. I will have to check. I thought I set the settings up where you could see that data, but if you can't, I'll look into it. Um anyway, but I believe the withdraw deadline is either Thursday or Friday. And with summer classes, unfortunately, it's just a reality where I tend to have those just because of the pace of the course. Just a reminder, while Homework 3 is due Thursday, it is basically moving some classes around, doing the bare minimum of some inheritance stuff, very, very little. And then writing 2 comparators and 1 comparable, and that's it. So I think that's a reasonable timeline for it. Homework 4 will be released on Thursday. It will involve what we cover on Wednesday and Thursday. And then Homework 5 next week will be released. The deadline for that will likely be Friday night, but I can look into how late I'm allowed to make the deadline. And that will there are still going to be Homework 3, 4, and 5. Outside of that, though, that's pretty much all I have for announcements. Any questions? All right, so let's start talking about stacks and queues. Now we've mentioned this term the stack before, and I've talked about the stack call frame, the idea that when you call a function, it puts another function call frame on top, and you're always running the one at the top. That's an idea of the stack, but we're going to try to make it a bit simpler than that. We're just going to talk about it as a data type. Um, so the idea is with a stack, it is a last in, first out, or a first in, last out system. The idea is the most recent thing put onto the stack is the first thing removed, and the thing that was put on the stack first is the last thing removed. By comparison, a queue is something that you're probably more used to. Like if you get in line at the grocery store, that is a queue. The idea is the people who've been in the line the longest are the first to get served, and therefore the first to leave the line. The people who've been in the line the shortest amount of time have to wait the longest. So this is last in, first out. The idea of the stack is we add and remove from the top, whereas a queue, we have a head and we have a tail. Things are added to the tail, things are removed from the head. Because you think, and the reason we say remove from the head, think of the head as the front, the tail is the back. You enter a line by getting in the back, you leave the line from the front. So a stack, for example, is you can think of it kind of like pancakes. If you were to eat pancakes one at a time, rather than just cutting up the whole stack and eating the stack in chunks, which admittedly is what I do, but if you were to eat one pancake at a time, you would eat the pancake here, off the top of the stack. You wouldn't get one out of the middle or one off the bottom, you'd start on top. Further, as the cook prepares pancakes, if they were to add them to the stack, they would add them on top. Another example, if you've ever worked in a kitchen at a restaurant, you often will see they have dish hoppers. The idea is it's like a spring-loaded device. You put the dish in, and the dish's weight kind of displaces the spring a fixed amount. So you just keep adding dishes to the stack. It weighs it down. So the dishes are in a nice protective sleeve. They don't get knocked over, and you just pull the top dish off. So whenever you wash a dish, you put it on top of the stack. Whenever you need a dish to put the food on, you take it off the top of the stack. So always adding and removing from the top. Any questions about that? And this code here is designed to describe if we were to make a pancake class, or not pancake class, excuse me, a stack class, we might start with a stack implemented as an array. That stack will say initially is size 3. We'll talk about whether or not we can grow this stack later. And then we have some pointer pointing us at the top. So going back to this diagram, the idea is we have this array representing our stack. The top is the first empty space. And we'll do a diagram here in a second of how that's done. So stacks have two primary operations: push and pop. We push things by adding them to the stack. So if we started with, say, an empty stack, and for now, don't worry about this grow if necessary. We'll talk about that in a second. The idea is we keep track of our top. Our top, again, is the first empty space on the stack. Then we are going to, give me 1 second. Also, just a quick reminder, the office hours queue should not be where you post questions. It should be where you post if you want to get into the queue. If you have questions, just post in general, or even better, post on Piazza. Anyway. So, first empty space, when we push, we add the thing that we're adding. So if we made, say, a stack of strings, we would push, if we called push hello, we'd push hello into 0.0, and then we would increment our top. So if we were to do a few different pushes, give me 1 sec, I have to reconfigure the camera here. There we go. If we were to implement our stack like this, we think of this array as kind of vertical, even though it's not, just because by illustration purposes, it kind of makes it easy. We think of our stack as vertical. This is still an array, by the way. And this array has indexes. Let's say my stack were size 4, or size 5 in this case. This is the capacity of 5. From there, initially this is my top. Let's say I were to push the words from Hamlet's soliloquy. So 2, and then we increment. And now this is our top, 1. Now, top's not a pointer, top is just an int, but it's helpful to draw it like an arrow, even though this is just an int telling me what index I'm going to next insert at. Then I do B, and I increment top, equals 2 now, or, again, insert at top, increment top, so on. This is pushing. Now you may be thinking, what happens when we run out of room? We're going to get there in a second. Popping is just the opposite. Popping is just the opposite. The idea of pop is I'm going to in the pop function. So push was void. We don't want to return anything with push. Push is just adding to the stack. With pop, we want to see what is being removed from the stack. So this is going to be E pop. In this case, E is a string, but E is whatever data type the stack is holding. So if the stack's holding strings, this is strings. The stack's holding integers, this is integer, etc. And with pop, we're simply going to decrement top. So top currently is equal to 3. I'm instead going to decrement it, so now top is 2 instead. And then I'm going to return whatever is stored here. In this case, what is stored here is 4. So I'm going to return that. Now, you may notice that the code I have here, if it says top equals 0, that means the stack is empty, so I'm returning null. That part should just be fairly self-explanatory. The idea is there's nothing I really can return, so I could either return null, or we'll talk later in the class, not today, but later on in the course, about throwing exceptions. But you'll notice I never do anything to delete the value. Or is still there. Why don't I set this equal to null? Why don't I need to do that? Anyone tell me why I don't need to set this to null? Or do something else with it? Why am I not worried that this or is here? Give a minute or so for people to respond. Right. The next time I push, let's say I were to push, it's to be or not. Let's say I push the word not. If I push the word not, here's what happens. I say stack top equals, so I say stack at index top equals not. That's going to replace this with not. And then I increment top. And now you'll notice that the or is just overwritten. I don't ever have to delete it, because if I ever reach that level again with pushing, I'm just going to overwrite whatever's there. Whenever you pop, you go down. Whenever you push, you go up. So if I were to pop now, I would remove not, but I don't need to delete it, because if I actually did need to go back up, I would do it by pushing. It would just overwrite whatever is here. Any questions about this? Pushing or popping? There's another function called peek. And peek is very similar to pop. But the difference is push and pop are destructive functions. Here's what I mean by destructive. I don't mean like, oh, let me just knock this lamp over. Actually, I did knock some stuff over. That was mildly destructive. Destructive means it changes the state of the object. Changes the state of the object. For example, back when we first did our first classes, we talked about Pez dispenser. The Pez dispenser function load was destructive because it changed the number of candies. Dispense was potentially destructive because it would potentially dispense a candy, decrement the number of candies by 1. ToString is not destructive, because calling ToString does not change the state of the Pez dispenser. Get candies or get num candies, also not destructive. So a destructive function is one that changes the state of the object. Push and pop are both destructive. Eek is non-destructive, or peek, excuse me, is non-destructive. And non-destructive means it does not change the state of the object. So with peek, what I want to do is I want to take a quick little peek at what is on top of the stack, but I don't want to actually delete what's on top of the stack. I just want to see what it is. Think of it like when you were a kid, you know, you maybe, depending on how good you were wrapping gifts, I was not. You might have been clever enough to like just open up and see what you're getting, and then like rewrap it and make it look like nothing happened. I have the artistic skill of a poorly trained chimpanzee, and so I never got away with that. But my sister was actually pretty good at it. Anyway. So how can we peek? Can anyone think of a way we would do that? How could we implement peek? And while we're looking at that, I'm just going to go ahead and open up Eclipse here. Where is it? Stacks and queues. This is what I want. Get rid of the top minus minus line and then return exactly. That's exactly it. So what I have here is I actually have stack code, and I effectively have the same thing as the slides, except some of these things are a little bit out of order. So one example is if I pop instead of returning null, I do this thing called throwing an exception. This is me saying you're not allowed to call pop if the stack is empty, that it will actually crash. But to match the slides up, we could say return null. We'll talk more about exceptions later in the course. But from there, then I could, so pop, I could store the string out as the stack top minus one and then top minus minus and then out. Or to match the slides, I could just flip these lines and remove the minus one. Both of these are correct. Neither is more correct than the other. With peek, public string peek, I would simply say, and technically I already have this function. No, I don't. With peek, I would simply say get the top element, which if we take a look at the whiteboard, you can see it's not the element at index top, because the value at index top is empty. So it's the thing below that. So, simply put, we just say return stack, return the stack top minus one. Now, can anyone think of an area where this approach won't work? Can anyone think of a situation where peek as written will not work? Right, if top equals 0. That is to say, if the stack is empty. And so to be consistent, I'm just going to use the same idea. If top equals 0, return null. So from there, I wrote just a quick little piece of code, print stack. This is just going to create a string output. It's going to loop over the elements of the stack. It's going to start by saying, just an open bracket, a closed bracket, I, and then for each element. And then from there, it's easier to show you what this prints like. So let's say I have, I push nada, then Lorna, then I print. Let's go ahead and comment all of this out for now. Then you can see I print nada and then Lorna. That's the idea. Hang on. That is not working as intended. Anyway, we'll look into that later. Anyway, so from there, if I were to add Jennifer to the stack, notice it adds Jennifer after Lorna in spot 2. From there, I want to show you what happens when I print. So I'm printing a line here because something special is going to happen. Namely, it's going to say growing. Now, why is this happening? Well, let's print the stack after we add Daryl. Oh, need to So after we add Daryl, but before we print, it says this thing growing. What is happening here? Well, let's take a moment. Let's go back to the whiteboard. One of the problems that we have is that every array has to have a finite size. And it's a fixed size determined ahead of time. And it just so happens, in this case, that our fixed size is 3. So we have index 0, 1, and 2, but we don't have index 3. Now, does that mean that, like a hotel, we say, sorry, we have no vacancy, and then just tell you, okay, you can't add it to the stack, piss off? No, we don't say that. What we do is we make room. And the way that we make room is we just build a bigger array. So we're going to create a new array that is twice the size of the old one. Twice the size. That is to say, we're going to create a, in this case, a string array. We're going to call this new array for now. And we're going to make it twice the size. So it's new string, and then our top at this point, because the array is full, is 3, which you'll notice is out of bounds. So we're going to say 2 times top. 2 times top. So this is new array. Whereas this variable here is the stack. New array on the right, the stack on the left. From there, we can simply iterate through this stack and copy all the values over. So 0 copies to 0, 1 copies to 1, 2 copies to 2, and now top is still equal to 3. And look, we have more space now. All we then need to say, after we do that for loop to copy, so I'm just going to write for, and this for loop's pretty straightforward. I'm not going to fill it in yet. After we're done, we simply say the stack equals new array. The stack equals new array. And now, this array is unreferenced. We've talked a bit about Java garbage collection before. We basically don't care what happens to it anymore, because now we're using this bigger and better array. And now I can do 3 more inserts. Question. You don't know why, but you feel you've seen this in video games. Well, you actually have seen this in something called array lists. This is how array lists work. Remember how we've talked about arrays are the underpinnings of an array list. But one of the questions that came up is, well, if arrays are fixed sized, then how do array lists allow for unlimited size? And the reason is whenever the array list needs more space, it just doubles the size of its underlying array. And it copies all the elements over. Now, one question is, why does it double? Why does it do that instead of just creating one space? Well, we're going to start talking about algorithms today. We're not going to get into what's needed to understand why we double, which is called amortized analysis. Amortized. And amortized analysis is basically a technique for kind of paying ahead algorithmically for work later. But suffice it to say that if we double in size, it has algorithmic benefits, whereas if we only increase by 1 each time, each addition gets more and more expensive. In short, kind of hand wave, don't worry about it, but understand this is actually how array lists work. They double in size when they need space. So let's take a look at that code within Java. So, the function that performs this is called grow if necessary. And what it does is it checks if the top equals the stack.length. That is the top pointer pointing above our current limit? Is it out of bounds? And if it is out of bounds, then we need to increase our stack size. So we double the size. We create a new array that's double the size. Then we loop over our stack up to the existing top. Just copying the new stack I equals the stack I. So 0 to 0, 1 to 1, 2 to 2, and so on. And then at the end, we update the stack to be the new stack. And as a result of this, you can actually see something useful here. I want to first print, I'm going to print here system.out.println, and I'm going to print s.theStack. And yes, technically this is private, but I'm still inside my stack class, so I can demonstrate this. So I'm going to print the stack here, and then I'm going to print the stack after I push Daryl. So actually, let me move it here instead. And what I want to show you, because remember, when we print an array, it prints the memory address. Actually, let's print it both times. Is that, notice, the array here, what is the address? 15db9742. 15db9742. What is it here? It's a completely different memory address. It is now a different array. The actual array that we're referencing is changed. Now, we've copied the values over, so we haven't lost any information, but it is a different string array now. Are there any questions about this? Is the top 3 by default? No, so in this class, I said the initial size is 3. There is no magic reason I picked 3. I could just as easily say 5 or 11 or 128. I could say whatever size I want. I have to pick a number, a positive number. I just picked 3 because I believe there's a song that says something about 3 as a magic number. I'll let you fill in the details. I don't remember. It's old. Older than me, significantly so. Might be from They Might Be Giants. It's kind of irrelevant. Anyway, this is grow if necessary. Why don't we just use ArrayList to represent the stack instead? You could, but if you used an ArrayList to represent the stack, all this code would still need to be implemented. The only difference is, instead of you implementing it, it would be Java. But I want you to know how this works. It's important to understand how the stack works. If you used an array list, might it be simpler for you from a coding standpoint? Sure, it very well might be. But I want you to understand that not just that there's an engine, but how that engine works. And so this is a way to show you not just how to implement a stack, but also this kind of unveils to you how array lists work. So when you call the add function of an array list, if the array list has no more space, if its underlying array, it doesn't even need to be a stack, it's still just an array, if that is full, it has a function like this to increase the size. And now you know how that function works. Make sense? Also, I don't know if pointing at the camera is rude. So if it is, I'm sorry. So could you implement this with ArrayList? Yes. There's nothing stopping you. You can implement it with a linked list. It's just the key is I want you to know why, or how, I should say. So from there, just looking at some other things. So let's pop a value off the stack. So notice that we add Daryl, and then we print the stack, and then I'm going to start popping. So I pop a value and print the stack. So you can see popping off the value Daryl is removed from the stack. Why do we remove Daryl instead of Nada? Because we remove the thing most recently added when we're talking about a stack. If I were to remove Nada first, we would actually instead be discussing a queue instead of a stack. From there, you can keep popping off. Oh, I need to delete the closing comment. And then you can see eventually we get to popping off, we have no more values. Any questions about the stack? And I want to be clear, the idea the stack doesn't have to be strings. A stack can be any data type. This array data type can be any object. It can be capital O object if we want it to be. The key is we just want to describe a stack at a high level. When we pop a value, we didn't delete the value. We don't need to. So I covered that a bit ago, how we don't need to delete the value. We just simply, because it's above our stack, whenever we push to get back to that point, we're going to overwrite whatever was there. You don't need to delete the value because you're just going to ignore it if you ever even access that index again. Because if you do access that index again, it's to do a push. Can you mix data types within a stack? Again, it depends on what you mean by that. By default, all collections in Java are homogeneous. You can make a list or an array of data type object and then use typecasting, but that's all you would be able to do. You wouldn't be able to say this is either an int or a string because it's a collection. It has to be homogeneous. But the way you can do it is, remember that you can say something like, this is a stack of type object, and then that means that pop will return object, but you could typecast that to any subtype, like string or integer. So you can use the hierarchies the way we discussed, but you can only make things one data type. So you'd have to make it the parent data type, and then you'd have to figure out how to do the typecasting. All right. I mean, I could put the string to, like, I could push that, but I can't push the integer to. But yeah, I mean, I did a demonstration with the hierarchies last time, so it'd be a similar concept as to what I did with the triangles or with the clocks in terms of what you needing to do that typecasting. All right, so this idea of a stack, it has a special, scary-looking name, and that name is called abstract data type. Abstract data type. Let's go ahead and write that down. Abstract data type. And it's often abbreviated to ADT. And when we are evaluating algorithms, as we're going to talk about later today, we do not evaluate ADT. Rather, we evaluate concrete data types. And I want to clarify what I mean by that. Concrete. Concrete is the opposite of abstract. This class that I wrote here, this is not abstract. This is a concrete implementation of a stack. It uses arrays, and we add to the end of the array and pop from the end of the array. I could implement a stack in a ton of different ways. I could implement a stack using arrays that we add to the front instead of the back. I could implement a stack with linked lists or with array lists. In theory, I could implement a stack with a tree, though it would take a lot of work to do that, more work than it's worth. The point is, I can implement a stack many different ways. Some of those ways are more efficient than others. This is conceptually a very, very efficient way to implement a stack. But it is not the only way. So understand that this is a way to implement a stack, not the way. You can implement a stack in a bunch of different ways. But why do we add to the end of the array? Why don't we add to the front? Can anyone tell me why wouldn't we add to the front? Why would that be a less efficient way? Why would it be less efficient to say add and remove from the bottom? That way we're always adding and removing at index 0. Exactly, because I would have to shift all the elements. So, hypothetically, and again, emphasizing this, hypothetically, I'm not saying I would ever implement it this way because I wouldn't. But just to show you what would happen, let's say I had a stack where I did always treat index 0 as the top. So the top will always be index 0. And the advantage is, now I don't have to worry about the top pointer. But, let's say I push 5, okay? And let's say there's a stack of integers. If I wanted to push 3 now, I would need to copy 5 down here, and then push 3. That took 2 steps. Now if I were to copy, or push 2, I'd first need to copy 5 down, then I would need to copy 3 down, then I would push 2. Now that took 3 steps. How many steps would it take if my array were size 100? Well, I would have to shift 100 values, or maybe 99 values, assuming the 100th value is the value I'm pushing. I have to shift 99 values and then do the insert. So, the number of steps it would take if I treated the top like it were 0, because it would require a loop, would be equivalent to the size of the stack. So as the stack gets larger, pushing would take longer. By comparison, let's take a look at our push function. Our push function only loops if we need to call grow if necessary. Or not if we need to call grow if necessary, but if the if condition for grow if necessary is true. And while you may think, well, that'll happen a lot, it gets exponentially more and more rare because of our doubling. And as a result of this, we can basically say, on average, this takes a constant number of steps. By constant, it means specifically it takes 1 and 2 steps on average. Technically, it's more than that, but the way it works out, it ends up being still a constant number of steps on average if you do a large number of inserts. Whereas, if we did like we did there on the whiteboard a second ago, where we insert always at 0, it will always take not a constant number, but a loop, where we have to loop over every element. So we'll talk more about that later. But so the idea of an abstract data type is just that, an idea. An abstract data type is an idea of how a given data structure should behave. That is, what functions it has, or behaviors. It is not an implementation. So given that, can anyone give me any other abstract data types we've talked about besides Q, because we haven't talked about Q yet, but we're going to. Can anyone think of another abstract data type we've talked about in this class? Emphasis on the word abstract. List, right? List is an ADT. Now, array list is not abstract. Array list is a concrete data type, because an array list is a list implemented in a very specific way. A linked list is not abstract. A linked list is a list implemented in a very specific way. But the abstract data type list describes, I have an ordered collection of things. I have a first element, I have a last element, and I have every value between. But list is interface. So is stack. Stack is an interface. It's still an abstract data type. Interfaces can still be data types. Comparable is a data type. We also have sets and maps. These are abstract data types. They can be implemented in different ways. Therefore, I cannot tell you how fast a list or a set is. I cannot tell you how efficient any of these are. Because none of these are implementations. They are ideas. They are descriptions of a set of behaviors. I can tell you how fast array lists are at particular tasks, and how fast linked lists are at particular tasks. I cannot tell you how fast a list or a set or a map is. So understand that abstract data type just means a description of a data set's or a data type's set of behaviors. And all those are collections, but comparable, also an abstract data type. Comparator, an abstract data type. So it can be interfaces. It can also be abstract parent classes. But generally it means a data type that only describes a set of behaviors, not any type of hierarchy or anything. So generally, it tends to be implemented as interfaces, though certainly not always. Any questions about this before we move on to Q? All right, a queue is a bit trickier. A queue is a bit trickier because, oh, gotta switch it to whiteboard cam. Because with a queue, we have to worry about two different sides. With a stack, we only care about one side, the top. With a queue, we're going to implement it like an array. And let's say you go to the grocery store. There used to be, often at the grocery store, you go like, if you went to the butcher's counter, for example, you would say, here, I want this, and you would take a ticket, and then that ticket number would be your order, and you would go do other shopping. You'd come back later and say, hey, I'm order 27. Something like that. The idea is the first person to get a ticket's the first person who's going to get their meat. In this case, you could think of this like a line in a movie theater. The front is where the ticket counter is. That is where you buy your tickets. And let's say when you arrive, there's 2 people already there. Well, you would love to just walk up to the front and go straight to the ticket counter, but we're not animals. We live in a society. Unlike Stuart, who is rubbing at my legs. We're not animals. We live in a society. You get in the back of the line. So if you're number 7, you get here. But the issue, the tricky part is this. Let's say 5 is done buying tickets. So we remove 5, right? Well, this is where this metaphor breaks down. Because if we're talking about an actual movie theater, well then 3 would step forward, and then 7 would step forward, and there'd be nothing here, right? But that's actually inefficient. Because that means that every time we remove a value, let's say this line were 100 people long. Let's say we're buying, I don't know, Star Wars tickets before we realize how bad Episode 9 really is. So we have a line that's that long. In that case, you don't want to have to iterate through this array and shift everything over. The whole point of how we implemented a stack was to avoid that. So we certainly want to avoid it with a queue. So the trick to this problem, let me take it back a step, is to, while you recognize the array is implemented this way, with indexes 0, 1, 2, and 3. And we're going to keep track of the front of our line. I'm just writing F for front. And the back of our line, I'm going to write T for tail. So front, tail. While we implement it this way, we visualize it this way. This is index 0, 1, 2, and 3. And the line goes clockwise. Now, 3 plus 1 is not 0. But we can do some tricks to work it out. Anyway, from there, we say, okay, 0, that's 5. 3, that's 1. 2, that's 7. If I were to remove someone from the line now, recognizing again that front and tail are two variables I have. Front is pointed to 0. It's the first person in line. Tail is pointed to the first empty space. If I were to remove from the queue, I would want to return this value 5, and I would do it by simply saying front plus equals 1. So now front moves up. And then I return the value 5. So I've returned that to calling function. Now, we can think of this as though it deletes the value, but we don't actually really delete it. So again, here's the visualization. Here's the actual state of the array. And the key is that now, let's say I were to add 4 to the line. So I in-queue 4. 4 would go where the tail is, and then we would say tail equals tail plus 1. Now, at this point, you might think, okay, we need to grow if necessary, right? We need a space here. But according to this visualization, we could just move tail clockwise, right? Because this is an empty space, so we're fine. So in this case, this is often referred to as a ring buffer. A ring buffer. It is still an array. It is not actually circular, but we do some simple logic to make it appear circular, so that when we need to insert 4, what we do with tail is we simply say, okay, tail plus 1. Oh wait, that's out of bounds? Okay, then let's wrap around, and tail is instead now 0. We wrap back around to the front. So this is the idea of the ring buffer. Are there any questions about this so far, before we get into actually implementing this? But an index 05 is still there. Right, it is in the array. And that's, but again, what would happen if I pushed 7? 7 would just overwrite the 5, right? I don't have to remove values because I will never use them again. They will simply get overwritten. What if the buffer is full and you add 1? Then you can grow if necessary. And we'll talk about how that's done in a second. But again, I don't care that the 5 is still there, because I think of tail as the end of the ring buffer, and so if I were to add a value, whatever value I add would overwrite the 5. No mess, no fuss. Alright, so with that, before we move on, the daily activity is actually relevant right now. So if you look, the daily activity is up, and it involves implementing a queue based on an implementation of a stack. Now, I'm going to do the daily activity in class, but I want all of you to get started on it now. So this will be an easy daily activity, because I'm going to do it for you. It's going to be done. You could effectively wait and copy my code. But I want you to take the initiative and try, and see what kind of pitfalls you run into. At least, if nothing else, take some time and try to diagram each of these behaviors. So work on that. You can also look at the slides, etc. Not all heroes wear caps. I sometimes wear a baseball cap, actually, and I'm also very much not a hero. Anyway, but we will take our break early in order to accommodate that. So go ahead, get started. The idea is you're going to be implementing, and again, this queue is actually already here, so you can just take a look at these behaviors and try to implement those, keeping in mind that you might need to handle wraparound. And we'll talk about that when we get back. I'll see everyone then. Not 2:19. It will be, what is 10 minutes from now? I'll give you the extra minute. It'll be 2:06 is when we come back. All right. Be back in a second.